In this video, we show an example of how to make a differential equation exact. In this example, we will make the differential equation exact starting from first principles. Now, the problem statement says, show that the given differential equation is not exact, then make the DE exact by multiplying by an integrating factor. And from this, we see that our integrating factor should be a function of y only. Then we're asked to show that the modified DE is exact, and we're told down here, do not solve the modified DE this time. We just want to do all of this here. We want to modify it so that it's exact, but we're not going to continue and try to solve the differential equation when we're done. Okay, to show that the given DE is not exact, the first thing that I would do is I would label these functions, the function multiplying dx and the function multiplying dy. In our class, we have tended to label this function m and this function n. Of course, different textbooks will label them differently. And then after you identify m and n, we'll want to compute those partial derivatives, the partial derivatives of these functions with respect to y and x respectively. So we'll start by doing that. Let m be the function multiplying dx and let n be the function multiplying dy. And then we'll compute the partial derivative of m with respect to y. So this is the partial derivative of 4x minus y with respect to y, treating x as a constant. If x is being treated as a constant, 4x is also a constant. The derivative of this constant with respect to y is 0, and the derivative of this implied -1 times y is just the constant coefficient, which is -1. And the partial derivative of n with respect to x is given by this expression. Now, I would just notice right away that y in the denominator is being treated like a constant in this context. So I would factor that out. And then think about taking the partial derivative with respect to x of x times y minus 4x squared. Well, if y is being treated like a constant, this is the derivative of a constant times x with respect to x. The derivative of a constant times x is just the constant, which is y. And then the derivative of -4x squared with respect to x can be found using the power rule. We have this -4 times the power, so it's going to be -8 times x to the 1 less power. So that's our partial derivative. And if we choose, we can write that as a fraction again, multiply straight across. And you've got that. Now notice that those are not the same. Since those are not the same, the current DE is not exact. Now, again, if you are using a different textbook or your professor is labeling these functions differently, the idea here is you want to take the derivative of the function multiplying dx with respect to y, and you want to take the partial derivative of the function multiplying dy with respect to x. That has to do with the mixed partials of that function f that we talk about in the other videos being equal to each other if the differential equation happens to be exact. Okay, so we see that these guys are not equal, so it's not exact. Then we're asked to make the differential equation exact by multiplying by an integrating factor where that integrating factor depends on y alone. So I would start by letting mu be a function of y, and then taking this differential equation and multiplying by mu of y. And of course, 0 times mu is just 0. And now let's assume that this resulting differential equation is exact. If it is exact, then the partial derivative of this function that's multiplying dx with respect to y has to equal the partial derivative of this function with respect to x. So we have mu times 4x minus y. Partial of that function with respect to y must equal the partial of this function with respect to x. And that's because the modified dE is assumed to be exact. Now remember, mu is a function of y only. So when I take the derivative of this, I'll use the product rule. This is my first function, and this is my second function. So what we'll have is the derivative of the first with respect to y. Oops, and that's an ordinary derivative because mu depends on y alone. Derivative of the first times the second, undifferentiated, plus the derivative of the second function with respect to y, times the first, undifferentiated. And of course, the derivative of this is -1, as we've already discussed. Now on the right-hand side, mu depends on y, not x, so we can treat that as a constant. This y in the denominator is also being treated as a constant. So if you want, you can factor out that mu divided by y. Again, because mu is a function of y, it's all constant. And then we're taking the derivative with respect to x of the xy minus 4x squared. And we actually did this earlier. If x is our variable and we're treating y as a constant, this is the derivative of a constant times x. It just gives us the constant, and then the derivative of -4x squared using the power rule gives us 8x. So now we have this. And I'm going to think of this as itself over 1 and multiply, and I'll factor that 1 over y out. And so I'm just rearranging this fraction times that fraction can be written this way. Now, if we've done everything correctly, this should be separable in terms of mu and y. Now you might be saying to yourself, how can that possibly be separable? We still have some x's in there. Hopefully, all the x's will cancel out. So the first thing that I would do if this is separable is add this mu to both sides. And of course, those will reduce. So on the left, we'll have 4x minus y times d mu dy equals this. Now over here, I could factor out a mu from everything. Looking at this expression and this expression, I see they have a mu in common, so I can factor that out. Mu times this gives me the first one. Mu times a +1 would give me that second one. Then I need a common denominator here. I'm thinking of this as a fraction plus 1. So I'll write that as itself over 1 multiplied by y over y. And so what we have here is y minus 8x over y plus y over y. So we add the numerators, keep the common denominator. course, we'll simplify. So I have 2y minus 8x over y. And I want to separate the variables. So I think I will divide both sides by mu to get my mu expressions over here with the d mu. Now I want to get rid of this 4x minus y on this side. So I'll divide both sides by 4x minus y as well. And remember, dividing by that is the same as multiplying by the reciprocal. So these guys reduce, and this is what we have. We've got, 1 over mu times d mu dy equals this. Now, if you're saying to yourself, do those even have anything in common? I think they do. If we factor out a -2 from that numerator, this is what we'll see. -2 times a negative y gives us that first term, and -2 times a positive 4x gives us that second term. And this is just that, just rearranged. So those undo each other, and we end up right here. Very nice. Now, the expression on the left is a function of y alone, because mu depends on y, and of course, d mu dy depends on y. So the only way this actually works is if this expression on the right is a function of y alone, and it is. So we can separate the variables, multiply both sides by dy, anti-differentiate from there, and sort of think of those as canceling, even though they're not canceling technically, just the definition of the differential of mu. We get natural log of the absolute value of mu over here equals -2 times natural log of the absolute value of y plus a constant of integration. I would do a little algebra from here. Now, from algebra, if we've got a constant in front of a logarithm, you can bring that constant inside. So I'm going to bring that inside there. And if we want to get rid of these natural logs, we might exponentiate both sides. So we'll have absolute value of mu on this side, because the log and the exponent, when they have the same base, those are inverse functions and they undo each other. So you just get a. Now over here, you've got a sum in the exponent. That's kind of like this exponent property for powers. If I have x to some power times x to a different power, I just add the exponents. That still works if the base is a number, if we're actually talking about exponential type functions rather than power functions. So if I've got a sum here, I can rewrite it as a product, It's going to be e to this power times e to that power. And of course, e to the c is just a different c. And if the absolute value of this equals this, then we can have a plus or minus over here. And again, the exponential and the logarithm with the same base undo each other. And so we get that. And of course, we only want one integrating factor. So I could let this whole thing be c, and I've got a y squared in the denominator. And of course, we only need one integrating factor, so we can choose any value for c that we want. Of course, we don't want to choose 0. I would choose c1 equals 1 to make mu as simple as possible. So we've got an integrating factor that depends on y only. It turns out to be 1 over y squared. All right, that was a lot. Before we go on, let's talk about what we did. We let mu be a function of y. We assumed that the modified dE was exact, and then we multiplied the dE by our integrating factor. And then we stated this condition on the partial derivative of the function of x and the partial derivative of the function multiplying dx and the partial derivative of the function multiplying dy. If the partial of this one with respect to y has to equal the partial of that one with respect to x. I'm just going to call that partial derivative condition for exactness. Basically, we're assuming this thing is exact. We say if that's actually true, well, then this has to hold. And then we do the computation. So then we evaluate those derivatives. See, everything that we've done here follows from these two assumptions. We're assuming mu depends on y, and we're assuming that our modified dE is exact. So provided both of those assumptions are true, we get to say this is true, which means we get to say this is true, which means we get to say this is true. And then we're just going to do some algebra. We're going to separate the variables. And since mu depends only on y, our hope is that all the x's will be gone after simplification. If all the x's were not gone, then actually mu couldn't depend only on y. We wouldn't be able to find an integrating factor of the right form. But we took our time to separate the variables because the problem was well written. We ended up over here and we ended up with this function of y has to equal this function of y, which is good. We did all the work of separating the variables. Once we do that, then we anti-differentiate. And then after that, we solve for mu. And you don't have to show all of these steps, but I included them just in case you need them. All right. So then we were asked to make the differential equation exact by multiplying by that function mu. So at this point, we're going to state our modified differential equation. Probably simplify it, and then we'll show that it's exact. So our original differential equation looked like this. We had 4x minus y times dx plus xy minus 4x squared all over y times dy equals 0. And we want to multiply this equation by 1 over y squared. And of course, 1 over y squared times 0 is just 0. So there's not really a need to write that over there. If I simplify this, I get 4x minus y over y squared here. And if I multiply straight across over here, I've got xy minus 4x squared. Y squared times y is going to give us a y cubed in that denominator. The claim is that this new differential equation is exact. That only works, or that's only true, if the partial derivative of this function with respect to y is equal to the partial derivative of that function with respect to x. Let's see if it's true. At this point, I like to label this new function multiplying dx to be m star and this new function multiplying dy to be n star, just to distinguish them from the original m and n. And then we'll compute the necessary partial derivatives. We want to compute the partial derivative of m star with respect to y and the partial derivative of n star with respect to x, and show that those are equal to each other. Oops, I'll let that be m star and let this be n star. So you could use Leibniz notation, you can use subscript notation, either one is fine. Since I've got a quotient here and the numerator and denominator, both depend on y, I'll use the quotient rule. So we do the bottom function times the derivative of the top function with respect to y, treating x as a constant. You'll probably remember from Calc 1, that's low d high minus high undifferentiated d low all divided by low low the derivative of this function with respect to y is -1. The derivative of that function with respect to y is 2y. And then we're dividing everything by y to the 4th. So what we have here is a -y squared. And then if I distribute a -2y to this, I'll have -8xy. And then a negative times a negative is going to be a positive y times a 2y. It's going to give me 2y squared all over y to the 4th. And of course, these two are like terms. They can be combined. 2y squared minus 1y squared is just 1y squared. Dividing all of this by y to the 4th. We can factor out a y if we want. You have that there, and then one of those y's will reduce with one of those. Okay, so that's the partial of m star with respect to y. Now we want to compute the partial of n star with respect to x. The 1 over y cubed, that factor that's implied there, that does not depend on x at all. So we can think of that as a constant. We can factor it out. And then the derivative of x times y with respect to x is just y, because we're thinking of that as a constant times x. The derivative of a constant times x is just the constant. And then the derivative of -4x squared with respect to x is -8x. So I've got this times that. We can write that as itself over 1 and multiply straight across. And we'll have that right there. Since those are equal to each other, we can be sure that our modified differential equation is exact, which is exactly what we wanted. Okay, that's it for this example. At this point, if we wanted to, we could solve this differential equation using the methods for solving exact equations, but we won't do that in this video. Please let me know if you have any questions.